All right, well, welcome everyone. I am JJ. Let's tackle an example problem. So we're saying let's use the method of joints to determine the force in each member of our truss that we have shown here. If we're starting that out, we need to figure out what are our support reactions. We can do this just using 2D rigid body equilibrium. We know how to do that. We've covered a ton of videos to tackle that. If we want to, we can go back and review some of those, but let's just jump in and go for it. So let's make a free body diagram. If I'm finding support reactions, I need a free body diagram of the entire truss that I'm working with in here. So we can get something that loosely looks like our truss. We'll get this drawn. I know we also have this. Boom, boom. At A, there's a pin right here. A pin should have a Y component, so I'll put in an AY. And I should have an X component in here, so I'll put in an AX. AY and AX. Each section in here is 6 feet wide, so I can get that labeled. This is 6 feet. This is 6 feet. Along the top, our first section is 3 feet, then 6 feet, then 3 feet again. 3 feet. I also need to get in my roller at C. I should have just one force perpendicular to what I'm rolling on. If that ground's horizontal, then I need one force perpendicular to horizontal. It would be a vertical force. So CY. And then my known forces. I have a 600-pound force in the bottom right of this. 600 pounds. And up here in the top right corner, there's an 800-pound force coming straight down. So we'll get that one added in as well, coming straight down, 800 pounds. And I can apply equilibrium to get all three of these unknowns, AX, AY, CY. Let's just come in and do that. So the first one I would do, let's sum forces in the X. Summing our forces in the X direction. I'm going to get 600. And AX goes to the left is what I guessed, so minus AX equals 0. Or if I solve that for AX, I'm going to get AX equals, my equation gives me a positive 600 pounds. When this solves to be positive, it means in my free body diagram, I guessed the correct direction. We're going to the left. And that would be, it's not an answer for us, but it's one piece that I need to be able to wrap up more of my problem. So we'll mark that one off. From here, I have two unknowns in the Y, AY and CY. I shouldn't sum forces in the Y then. Let's do moments. If I can get my moment figured out to get one of these two, then I'll sum forces in the Y. So let's come down below and I'll say with positive, going counterclockwise, why don't I sum moments up about A? That'll give me CY. There's other points. If I'm looking for one of these, I get sum moments at C. I get AY then. Just choose one of them though. But summing moments about point A, I'm going to have 6CY. My 800 pounds will cause a clockwise rotation, so minus force is 800 times my distance will be 3 plus 6, 9. And my 600 pounds in AX don't cause any moment. So I can set this entire equation equal to 0. If I solve, I'm going to get that CY is 1,200 pounds. And it's going upwards. Finally, my next piece would just be to say with CY known, why don't I sum forces in the Y and I can get AY. Summing my forces in the Y direction. I get AY, my final unknown, plus CY, I know goes up, 1,200. Minus 800 is going to get me to 0. If I solve that for AY, I'm going to get that AY is negative 400 pounds. And that's when I guessed that it went up. We always want to work with our force as a positive and get the right direction. So when we recognize that that was the wrong assumption, we're going to come in and say, let's put in a dashed arrow to show this is really going down. When we use this in our next steps in here for the particle equilibrium, our method of joint section of this, we'll assume AY is really going down because we know that. Then we'll report as a positive. AY is really a positive 400. We're dropping that negative. Our units are the same, but our direction is really going down. Get our positive with the correct direction in there. That's our support reactions. This should feel like a review from rigid body equilibrium, because really it's just building off of that a little bit. Our new piece is doing method of joints in here. So I want to look at my truss and every pin in here where our members are coming together. I'd have 1, 2, 3, 4, 5. Really, it's every point that's named. A, B, C, D, E. I could apply 2D particle equilibrium. Some forces in the X, some forces in the Y to solve that out. My forces will show up in here, and then any member that connects is going to be an unknown force. Just one force that goes right along the member. So what we want to do is come in and say, where do I have two unknowns and something that's known, or fewer unknowns? I could do that at point A. If I were to circle around A for my free body diagram, I would have my pin, so I need to include AX, AY, and then my circle cut through AB and AC. So I would have to put those in as two unknown forces for us, an FAB and an FAC. I could solve for both of them. If I went to B, I would have AB, BC, BD, three unknowns. I only have two equilibrium equations, so I couldn't solve that out. If I went to C, I would have AC, BC, CD, CE. My roller would also be there, even though it's known. I'd have five forces, four of them are unknown. I couldn't solve it. At D, BD, BC, or BD, CD, DE, and a known 800-pound force, still three unknowns. I can't go there. Or I could go to E. I would have DE, CE, and a known 600-pound force. I could find everything there. Really, on this one, I want to start either at A or at E. Either way, I'm going to eventually get to the same answer for everything. So just go with one of them. I'm going to go to joint A. So I'm going to come down below and start drawing this in. This is particle or joint A. I need to put in my AY and my AX in here. I know AX, I found it was really 600 going to the left. So that'll be one piece I want. This is 600. 600. I also need AY. I found it's really going down when I found my support reactions. So I'm going to show it going straight down. Taking that positive with the correct direction. It's 400. We cut through member AB, so we're going to show it. We always assume tension on our trusses. So this is an FAB, the force in member AB. Always assume tension when we're doing truss problems. It goes out from A. Our other one would be an FAC. We cut through member AC in here. It also will be an unknown in our free body diagram. And the last thing that I need is this angle right here. What's my angle theta? If I find theta here, I actually have that angle for pretty much every step. That's the same, or that is my angle right here for theta. But that's also this angle, theta. That's also this angle would be theta. This one would be theta. This one's theta. And all the way over here, this one is theta. All of those are the same angle in here. Every single time it is theta force. So if I get this at one point, it really is a useful thing for me throughout the entire problem. I have angle theta over and over and over showing up in this. That's going to be true a lot of times for trusses, that the angles show up over and over. All of these are members going over 3 feet and up and down 2 feet. And I can find theta just using trig. That theta should be, theta is the inverse tangent of opposite over adjacent. Remember, AB goes, opposite would be 3 feet. Sorry, opposite would be the vertical, up and down is 2. Adjacent would be 3 feet. 2/3. The inverse tangent of 2/3 is going to get us 33.7 degrees. With that known, I have FAB, FAC. I can sum forces in the X and the Y, start finding my unknowns. So which one of those do I want to do first? Should I do forces in the X, forces in the Y? There is a clear, better answer for this. If I sum forces in the X right now, I need to include FAB and FAC. I can't solve for those. If I sum forces in the y, though, I only have FAB, one equation, one unknown. Start there. Take the time to think through what's a smarter approach for me here. Don't be the person who tries to just blindly start with the x. There's no value in it in this one. And it's way easier if we do y first for this. So we'll start there. If I sum my forces in the y direction, we're going to get here that I have the y component of FAB. So FAB times, I want the sine of my angle. Sine 33.7. The only other y force I have is that 400. So minus 400 is going to get me to 0. Equals 0. When I solve for FAB, I'm going to get here that FAB, the force in member AB, is a positive 721 pounds. Which for trusses, all of our truss members are either going to be in tension, if they're getting pulled apart, or they're going to be in compression, if they're being squeezed in. We will always report our truss members as a positive, and then we'll say T for tension, C for compression. So I assume tension to start out every time. I got a positive answer here, which means I am in tension. So I can box that as an answer. And then we can move on and take a look at our x components. Summing our forces in the x direction. I can say, well, I have FAC entirely to the right. FAC. I have the x component of FAB plus 721 cosine of theta, 33.7, minus 600. Minus 600 gets us to 0. If I solve that one, FAC is my only unknown. I get kind of this weird situation happening where FAC ends up being 0. From a design standpoint, technically what we're saying here is we could remove FAC from our truss and it wouldn't change anything. From a practical standpoint, though, and how we'd actually design it, not just like a theoretical standpoint, we want to keep that member in there because very rarely are we going to have everything perfectly aligned like this. And if it wasn't this exact situation, things will start to fall down. And we don't want our trusses to fall down. Or if you think of this as like a bridge in here, maybe it's a little pedestrian bridge that we can walk across. If we took this member out, all of a sudden there's nothing for us to walk through. People fall through the bridge. It's never a good situation. So we'd want to keep that in there, but it's not actually supporting anything. That's okay. That will happen from time to time for our trusses. That finishes joint A. Let's come in over here then and say, well, where do I go now? I could still go over to joint E. We could have started there. Still true. We could go there. Now I could actually go to joint B, though. I know FAB, so at point B, I would have FBC and FBD, just two unknowns for us to work with. I could apply equilibrium and find both of them. So let's go ahead and try that one. We'll get this one figured out, and then we'll pause and erase a bunch of stuff. But if I go to joint B, drawing in my joint here, I'm going to have at B, I would have in tension. We found it was in tension before, so it's still in tension now. I'm going to have an FAB. It's going to go down and to the left, away from our free body diagram circle, away from the joint we're looking at. Really, I could have come in and circled right here for my free body diagram circle. If it's in tension, it's leaving that circle. If it's in compression, it'd be squeezing into the circle. We know this one's in tension. FAB equals 721 pounds. If it was in tension before, still in tension now. And our angle on this is still theta. It also hasn't changed for us, still 33.7 degrees. I have member BD. I'm assuming tension because I always do that for trusses. So I have an FBD in here. And one more time, assuming tension, because still always we do that for trusses. I'd have an FBC at an angle theta. And I found that. That's the same angle theta as before. I have two unknowns in here, FBD, the force in member BD, and the force in member BC. I have two equilibrium equations, forces in the x, forces in the y. I can find both of these. So let's come in and do equilibrium. If I sum my forces in the y direction on this one, summing forces in the y, I have Well, FAB acts down, so negative 721 sine 33.7 sine theta. And FBC acts down, minus FBC sine 33.7 equals 0. If I solve for FBC, I'm going to get FBC, the force in member BC, equals negative 721 pounds. That negative means when we assume tension, we weren't right on that. It should be in compression. So at this point, we'll come back in and, kind of like we did with our support reactions, we'll put in a dashed arrow on everything, saying, hey, when we started this problem out, I assumed it was in tension, because we always do that. I just found this one's really in compression, though. So any future equation, I should set up and use it acting, if I'm looking at B, up and to the left for this. And then our report is a positive, FBC is a positive 721 pounds in compression C. And that'd be our second or our third answer for our problem. The first one from this joint. With FBC known, I can now come in some forces in the X to get FBD. So summing my forces in the X direction. I have FBD, my final unknown from this particle, plus the X component of FBC. Sorry, not plus, minus, because it acts to the left. We know it's in compression. It's really going up and to the left. So in the negative X direction, minus 721 cosine of 33.7 minus FAB's X component, minus the exact same thing, 721 cosine 33.7 gets us to 0. Technically, we could have just said times 2 in here. I avoid doing that when I am just summing up forces, because if I have 721 cosine 33.7 times 2, when people look at my work, it looks like for some reason I stuck a moment in here, and it just confuses everyone. I would rather write it out twice. It sets me up to be more successful. It helps anyone reviewing my work also more effectively review my work, and just makes me look like I'm more competent. So I do it that way. There's nothing wrong if we just said times 2, because there are 2 of them, though. But FBD is going to solve out to be equal to, on this one, where is it in my notes? 1,200 pounds. I'm getting a positive number here, so we are in tension for this, which would be our fourth answer for everything. From here, again, we can keep going with that. I have done joints A and B. If I go to C now, I know FAB, I know FBC, I know CY. I found that way back at the very beginning of this. I would just have FCD and FCE, 2 unknowns. I could find both of them. Or I could go to joint D. I would have BD as an unknown. I'd have, or BD I just found, FBD. So I'd have CD and DE, 2 unknowns in here. Either way works for us. We're going to have to do 2 more joints in here. I'm going to erase kind of where we've come from this so far, just so we can reset that and keep going with everything. I'll get the numbers we found rewritten in here, but let's pause really quick and come back to take a look at that. So we've done joints A and B. Again, we mentioned this before. We can move to C or joint D in here. I'm going to choose to move to joint C for this. So we'll come over here and we need a free body diagram, because we know we're going to apply an equilibrium equation. Anytime we use an equilibrium equation, we need a free body diagram that goes with it. So I'm going to get in C in here. I found CY back at the beginning, doing our rigid body equilibrium of the entire truss, was 1,200 going up. So that's still true for us here. CY was 1,200 pounds. We also have here, let's just get in, I'll go counterclockwise around this. Going straight to the right, I have member FCE. It's unknown, so we'll assume tension, FCE. I also have going up and to the right, member CD. It's unknown for us, so we're assuming tension, FCD. And that should be at an angle of theta, which I should have written down. Theta we found before. Theta was 33.7 degrees. Was another one of those useful pieces for us. because it shows up all over in our truss. We have going in compression, we have member BC coming in here. If it was in compression before, it's still in compression here. So this should be acting, instead of away from our free body diagram circle, we're squeezing into this one. It's coming down into that. Is our FBC equals 721. Then finally we have member AB in here. We found, AC. Remember AC. AC was 0. So I'm just going to leave it off. Or I could put in an FAC and say it's 0. But I need to label this angle. This is also theta for us. Two unknowns, FCD and FCE. I should be able to find both of them as I come in here. Just applying equilibrium for this. So why don't we come in and say, why don't I sum forces in the y direction to start this out? If I sum up my forces in the y, I'm going to have 1,200 going up, 1,200. I have FBC coming down, so minus 721 times our sine of theta, sine 33.7, 33.7, plus our y component of FCD, plus FCD is unknown. FCD sine 33.7, and that's getting us to 0. Just 3 things to get in there. We can solve this for FCD, our only unknown in here. We should get that the force in member CD is negative 1442 pounds. That was negative when we assumed in our free body diagram that it was in tension. We just found it's really in compression. It's squeezing into this joint. So I should put in that dashed arrow showing I now know which direction it's really going. We're not erasing that original because we have work that was based on that. But we'll use this dashed one for anything moving forward. And we'll report our answer as a positive. FCD is a positive 1442 pounds in compression. Always giving our truss members as a positive with either T or C, depending on which one it worked out to be. But then I can sum force in the X, and I'll get FCE out for this. So summing forces in the X direction. I have FCE to the right. I don't need to put CY in here. I need to put in the X component of FBC plus FBC, we know, 721 plus 721. And we know it's in compression, so it's pointing to the right. So we add it, 721 cosine 33.7 theta. And we'll subtract out FCD's X component, or minus 1442 cosine of 33.7 gets us to 0. Which if we solve that for FCE, I'm going to get here that the force in member CE is 600 pounds. And we are in tension for that. Finally, our very last thing that we need to do, we can go to either joint D or to joint E. Again, there's 2 options for this. There's multiple ways we can solve out these truss problems. We just want to pick one of them. I'm going to go in and tackle joint D. So we need to include, if we circle it, it looks like I need my 800-pound force, and I cut through BD, so that'll be there. I know BD, though, is 1,200. We cut member CD. I also know that one, 1442. And I cut member DE. Really, there's one unknown left for me to find in here. So we can come over and get this sketched in here. This is joint D that we're working with. I know I have 800 pounds going down. I have, it's unknown, so I'm going to assume tension, an FDE, the force in DE, at some angle theta. I have member BC up on the top here. FBC I got was 721 in compression. If it was in compression before, it's still in compression here. I don't want BC though, I want BD. If it was in tension before, grabbing the right member, we still have it in tension. This is FBD is 1,200. And our final force that I need, I cut member CD in here. I need that one. CD, this one was in compression. 1442 in compression. If it's in compression here, then it's still in compression at the other end of the member. FCD is 1442 at an angle theta. DE goes in the Y and the X direction. Really, I could use either equation here and solve for FDE. It really doesn't matter to us. We just want to choose one of them. If we sum forces in the X for this, is what I decided to choose. Summing forces in the X, we would have FDE cosine theta, 33.7. I'd add in FCD's X component plus FCD, because it's going up and to the right in compression, 1442 cosine 33.7. And then minus FBD, minus 1,200, gets us all the way back to 0, equals 0. Solving for FDE, our very last unknown in here, we get that this is another zero force member. FDE equals 0. If it's 0, we don't need to put tension or compression on there. It's neither really. It's not in tension. It's not in compression. It's just 0. But that'd be our final answer for this. Method of joints is really just a bunch of particle equilibrium problems. If we go slow and steady as we progress through this, we know how to do particle equilibrium. We're just summing forces in the X and the Y. We can get through everything in here. Take your time with it. Just slow and steady as you go. But good luck with that. If this was useful, hit the like and subscribe buttons. Stick around. Let's get you an A with JJ.